Our journey begins with the revolutionary discoveries that have transformed our understanding of worlds beyond our solar system. The 2025 Exoplanet Revolution. In March 2025, the James Webb Space Telescope achieved a breakthrough by directly imaging carbon dioxide in the atmosphere of HR 8799's gas giants, marking the first time we could fingerprint exoplanet chemistry through direct observation rather than transit methods. This milestone represents just one achievement in a year that has brought humanity's knowledge of distant worlds to an unprecedented level. Astronomers have now confirmed the existence of over 6,000 exoplanets scattered throughout our galactic neighborhood, with thousands more candidates currently undergoing verification through multiple observation methods. This represents a dramatic expansion from just a few hundred known worlds 2 decades ago. The rate of discovery continues to accelerate as our detection instruments become more sensitive and our analysis techniques more sophisticated. The James Webb Space Telescope has fundamentally transformed how we study these distant worlds. Webb captures starlight filtered by planetary atmospheres to fingerprint molecules like water, methane, or carbon dioxide. This capability has revealed water vapor signatures on multiple potentially habitable planets within our cosmic neighborhood. The concentrations of water vapor on these worlds suggest the presence of substantial atmospheric moisture, and in some cases, possible surface oceans. Recent atmospheric analysis has detected intriguing chemical combinations in several exoplanet atmospheres. Researchers have identified unusual concentrations of oxygen and methane that are difficult to explain through purely geological processes. The presence of these gases in combination suggests the possibility of active processes on these worlds, though definitive biosignatures remain elusive. The silence from these worlds remains absolute. Despite decades of monitoring radio frequencies and searching for artificial signals, these potentially life-bearing planets emit nothing but natural electromagnetic radiation. New spectroscopic analysis techniques have allowed astronomers to identify atmospheric signatures with unprecedented precision. Advanced computer algorithms can now detect oxygen and methane simultaneously in exoplanet atmospheres, a combination that on Earth indicates biological activity. Several planets within our immediate cosmic neighborhood show these dual signatures. The oxygen concentrations on several of these worlds exceed what geological processes alone could maintain, suggesting active replenishment through photosynthetic or other biological mechanisms. The methane detections are particularly intriguing because methane breaks down rapidly in most planetary atmospheres through photochemical reactions. Its continued presence indicates ongoing production from either geological or biological sources. On Earth, approximately 95% of atmospheric methane comes from living organisms. The detection of methane on multiple exoplanets within our immediate cosmic neighborhood raises profound questions about the prevalence of life in the universe. Survey data from multiple space telescopes has confirmed that roughly 40% of red dwarf stars host planets within their habitable zones. Red dwarf stars comprise about 75% of all stars in the Milky Way galaxy, making them the most common stellar type. This discovery has dramatically increased estimates of potentially life-bearing worlds. The Milky Way contains approximately 100 billion red dwarf stars, suggesting that 30 billion planets might exist within habitable zones around these stars alone. The mathematical implications of these discoveries are unsettling. Current detection rates suggest we identify new potentially habitable planets every few weeks. Statistical models based on this discovery rate predict that we should encounter definitive signs of life within the next decade if life develops on even a small fraction of suitable worlds. The probability calculations indicate that continued failure to detect life becomes increasingly unlikely as our catalog of habitable worlds expands. Advanced computer modeling has revealed another disturbing aspect of these discoveries. Many of the potentially habitable worlds we have identified appear to have maintained stable conditions for periods far exceeding Earth's history. Some planets around red dwarf stars may have been habitable for 8 to 10 billion years, providing enormous timescales for life to develop and evolve. If life follows similar evolutionary pathways on these worlds, some civilizations could be billions of years more advanced than humanity. The age disparity raises uncomfortable questions about what should be observable in our galaxy. Civilizations with billions of years of technological development should have achieved capabilities we can barely imagine. Their absence from our detection efforts becomes more puzzling as we discover more ancient, stable worlds that could have supported such development.